Okay, so today I'm going to talk about the photolithographic 3D nanopatterning platform. Platform technology is generally useful for collaboration. So luckily last year, my group was awarded that special funding resources from the Korean government, and then we founded a center for the control of material properties by 3D nanostructure designs. So our center is actually supporting this workshop, and hopefully today, through today's talk, some of the Singaporean students and also professors at NTU, we can initiate some collaborations. Okay, so today my talk is briefly have three parts about the overview of our group's three-dimensional patterning technology. And second is some recent examples of how our 3D structure initiates some collaborations and some scientific works. And finally, current direction of my research and our center's goal will be presented. Okay, so this is probably some of the people already see, but this slide is one of my favorite slides. So the first image, second image, and third image, maybe some of you are familiar with. This is the cross-section of seashell. And this is the cross-section image of peacock's feather. And this is cross-section image of the interconnects in the microprocessor chip. What I show you those three examples is actually in the nature, we have very beautiful 3D nanostructures. And then these beautiful layered structure make unusual mechanical properties. And this beautiful optical structure make unusual colors. And also all those circuits above the baseline CMOS enables us make some like the brain-like functioning. So all these beautiful techniques possible because some nanostructure is allowed. But unfortunately, this price of microprocessor is very expensive, so everybody wants to make this. But the others, even though we like seashells and beautiful colors of peacock, if somebody asks you the price of a microprocessor, nobody will buy it. So actually, because of nanoscience, nanotechnology, we now have some tool make three-dimensional nanostructures, but still the cost and speed and things are one of the determining factor applying those three-dimensional structure in new science and new technology. So my group has certain platform technology to make large areas three-dimensional nanopatterning structure. So that's my take-home message today. And this is the Marina Bay in Singapore. And actually, when you take a look at around our surroundings, everything is three-dimensional. And but still, one interesting thing is how beautiful this building is. All the building, the making procedure, construction procedure is layer by layer. So this image here is actually world's largest 3D printing. Some European company, they are actually trying to print houses. So this tells my scheme. So even though we want to make complex three-dimensional houses and buildings, everything should be just layer by layer, line by line drawings. So is it possible if we can make this three-dimensional complex structure in single shot of patterning? This can be very fast, right? This example is not only applicable to those buildings. In this small size scale, when you take a look at this microprocessor chip, this is definitely very complex three-dimensional structure. But the bread and butter of this technique is photolithography. Photolithography is basically, there is photoresist and there is mask, and then some mask blocks light, some mask transparent, make the light pass through, and then some of the chemical change in the photoresist make the two-dimensional structures on surface. And then simply to making this, we are stacking up those procedures. But why? This is relatively more expensive but still people keep working on. The art EUV machine. Do you know how much one single machine of this ASML EUV lithography tool? Anyone has some idea? Actually, at the beginning, somebody predicted it can be 1 billion, but fortunately, it's much cheaper now, $200 million per machine. So actually, if you can have $200 billion just for one machine, wow, it's very, very expensive. But still, people keep following the trend of photolithography on these microstructure processors. The reason is actually the productivity. When people sometimes think about resolution, maybe it will be much easier. What 10 nanometer resolution means. In current semiconductor processor, we require 10 nanometer resolution or less than 10 nanometer for the next business cycle. So you are pretty familiar with DPI, dot per inches. So your high resolution camera usually has about 1000 DPI or 500 DPI is generally good enough. That means you can put 500 points or 1000 points in one inch length. So 10 nanometer resolution in one inch, actually it means near 2.5 million DPI. And then if you conventional semiconductor photolithography process requires 1 inch square patterning. So if you have square array of that, actually it means if you want to get perfect 10 nanometer resolution image, it is almost like 1.25 times 10 to the 13 bit. And if you change it to the byte, it can be 1.5 terabyte. So that means basically one single shot of exposure, you are transferring the information of 1.5 terabyte in single shot of photolithographic process. So that's really, really fast. Imagine if you have the mobile hard drive and then if you transfer the data 1 terabyte from one place to the other, it usually takes a couple of hours. But this using photon and then shining the light and transferring rate of data is unbelievably high. So that's the beauty of optics and photonics. So, but still, everything is two-dimensional. So my group has been actually developed some new patterning technique, making three-dimensional structure. So instead of conventional amplitude mask, we make certain surface roughened transparent mask, and then using special optics. Because of the time constraint, I won't explain it deeper, but using this special mask, and we can make conformal contact, and then we just shine the light. This type of interference patterns can be recorded into the photoresist. So if I just simply extend the argument of that resolution, so even in simple two-dimensional planar cases, it can be easily 1.5 terabyte if the resolution is 10 nanometer. But if you can extend to the G direction, the film depth of photoresist, actually it can be easily 100 terabyte to or petabyte or something like that. So that complex intensity distribution can be generated and recorded into this photoresist, and we can make very beautiful three-dimensional nanostructure in large area and large scale. So if you are interested in this, in our group's proximity field nanopatterning, actually this was my PhD thesis in 2003. And then from that time on, my students and my group has beautiful heroic work, and by extending the mask designs, and then so we can make some hexagonal, square, or even quasi-crystal, or some beautiful diamond symmetric structures. So we designed mask design a lot, and also not only these optics, we also working on the materials and patterning strategies. We have developed this technique over almost like now almost 20 years. And production area wise, as I just mentioned, if this can be the platform technology, then we must be able to make the 3D patterning in large area, larger volume. So anyhow, this summary of our group's work and the general optics explanation was published on Nano Research Journal of Nano Research Journal. Actually, this is special issue of Professor John Rogers, who awarded the highest nano award in China, and then this special issue is only contribute to his students and postdocs. So our paper was one of the invited paper there. So if you are interested in, please consult this one. So that's the, I just skipped the PnP's overall optics and things. Anyhow, so the most important, today's my topic is platform. I just want to briefly show our production area increase effort. And this is actually around 2010 when I just joined KAIST. KAIST has a world facility nanofab center. So actually we was able to make 1 inch by 1 inch phase mask. So inside here about 200 to 300 nanometer dots are like almost like the 100,000 times by 100,000 times, something like that. So we can put those and then make the diffractions. And we were able to make this 1 inch by 1 inch whitish structure. So when you first take a look at these images, yeah, this is some whitish crab or trash. But if you just cross it, if you just break it and see the cross section, you can see that there is about a couple of 100 nanometer pore structures. They are not only single hole, they are all interconnected in certain symmetry. Here we can say this is body-centered tetragonal symmetry. So we can able to make this large area, three-dimensional, ordered, porous polymeric structure. So at this time we claimed this is a man-made world largest submicron porous ordered structures. So from that, actually this is a kind of the more recent work. You can see here some transparent film, and then this is my student finger, and then if you stretch it, this become opaque. So this is kind of mechanical scatterer, and then this definitely, I don't want to go detail about this work. So if you are interested in, check out this paper. But what I want to show you here is, yeah, now our three-dimensional porous structure can be in this size scale, couple of inches by couple of inches. So basically, the size of three-dimensional patterning area we can make, it only depends on the size of the mask. So we can actually extend the size scale more. So, but after we making this polymeric structure, people's question was, okay, I agree, you can make some interesting polymeric 3D structure, but what this is good for? Yeah, so because as a material scientist, we are more interested in metal or semiconductors or some oxides for various applications. So to answer that requirement, actually we developed a lot of technique that after we making those three-dimensional submicron porous structure, we did some ALD or some deposition technique, or we also do some electroplating. So this is the example. If you do the ALD, all the complex surface of our 3D structure can be coated with oxide or metal, and then after burn out the polymer, we can make this 3D interconnected thin shell oxide structure. Or sometimes if we just infiltrate the electroplating of metal, and then we burn out the polymer, we can make these three-dimensional porous metal structures. So basically, the material we can make is not limited by our polymeric structure, but more limited by the source material. We can do the electroplating or ALD. But basically, we tried most of those sources, and then we have pretty good wide variety of three-dimensional metal structure and ceramic structures now. So this is the example. So actually the beauty of this AL technique is depending on the number of cycles you depositing time, so you can precisely control the thin shell thicknesses. Here, this is 300 cycle equivalent to about 30 nanometer thin shell thickness here, and then total film thickness about 10 to couple of tens of micrometer. And this 500 cycle means 50 nanometer, 770, 990 nanometer. So we can make three-dimensional thin shell oxide structure. This is TiO2 and aluminum oxide. And also not only with those oxide, we can also make this metallic three-dimensional porous structure. So if you check out the current technology, you can find out the nickel porous mesh, which has about a couple of 100 micron porous structure very easily. But if you want to buy some nickel or copper or whatever material, metal, in a couple of 100 nanometer ordered porous structure, it's almost impossible to buy. So actually our group has the capability to make this ordered metallic porous structure. I'll show you a couple examples later. And also not only we are satisfied that, we go further. And actually this is gold hierarchically porous structure. You can see here that the gold has a couple of 100 nanometer PnP defined structure, and also it has some tens of nanometer micro porous structures together. So definitely this one has a couple of 100 nanometer macro pores and tens of nanometer micro pores. So we call it hierarchical porous structure and find out some interesting application. One step further, we are working also with some groups at KAIST, like professor in chemistry department. We also put some copolymers, and also Professor Taeyeon Baek. Actually, he was the professor at NTU in chemical engineering, now moved to KAIST, and we're working together. And then we also make the hierarchical porous MOF structures. So using this, we can make some new application and new sciences of nanoscience. So I'll just show you, we have numerous examples and application, but I'll just show a couple recent applications. So if you are interested in our application, actually we not only use it for the nanochannel, microfluidic system, photonic films, and energy application of piezoelectrics, gas sensor, batteries, and also all the scattering. So depending on the size, what we made, the three-dimensional platform, technique, depending on the size scale, all the application requires different size scale. So what we are trying to do over the 20 years, we are trying to cover all those people's requirement for the three-dimensional structure in size scale wise, we answered. So those examples can be found from this paper, so you may check out that. And so this is one of my favorite movie. So, you know, I made the three-dimensional thin shell oxide. We just FIB and cut it out. And then if we press it, this is actually ceramic. So yesterday, some flexible electronics professors already mentioned that silicon and most of the inorganic materials, they break within 1 or 2% of strain, right? But this is more than 10 to 20%. So this is work with Professor Dongchan Jang, and also we use this type of thin shell 3D structure with Professor Seung-Bom Hong for piezoelectric application. But one thing I want to show you here is the material, the stretchability or certain elastic limit is material's intrinsic property. But if you apply some these new structural symmetries or structural constraint inside, actually the same material can be more stretchable or sometimes even avoid the breakdowns. So this is our group's philosophy of metamaterial. Using the same material, instead of controlling the composition or the atomic bonding, simply adding the structural factors, we can generate new material properties. So actually this material can be very useful. One of the very well-known old topic of mechanicals is HB plot. So here strengths and their material density. So generally speaking, heavier material is more stronger, and forms like the very lightweight material is weak. But if we can use that good materials in three-dimensional porous structure, actually we can run away from their material's limit. So this means our three-dimensional oxide structure, which is in density-wise close to foams, but their strength is remaining close to the most of the polymers, even to some ceramics. So we can make lightweight material, and we can avoid the material's limit governed by Asheville plot by structural designs. And also, this is one of our recent example that we just use those three-dimensional porous oxide thin shell for sensing materials, and then we found out this three-dimensional TI what shows the highest responsibility ever in anode sensing. So in these cases, the reason we can achieve this perfect, very high sensitivity, even at room temperature under humidity condition. If you're a sensor scientist, room temperature and humid condition, generally sensors become very erroneous. But our light-driven anode sensing sensor has good sensing capability because it has large surface area. Also, we are detecting the gases. So gas detection, we need large surface area. Also, if the pores are blocked from the top and down, we cannot utilize whole bottom parts of the materials. So continuous open 3D network is key of the success of these examples. Okay, so also because we also had some collaboration with Professor Xiaodong Chen, so I just added a couple slides here. So when you take a look at the electrode in energy conversion system, especially electrochemical energy, generally those electrodes are very primitive old science and technology. Just make people some powder and then pack it. For example, lithium-ion battery, their cathode material, oxide particle, they just mix with some conductors and then pack it. That's it. So our group is thinking about, is there any better way to make better energy conversion efficiency of, especially in the electrochemistry? So we think about making some good 3D structure or even hierarchical structure can be beneficial for many applications. So here is one example. So gold is very well known CO2 to CO conversion material, but opening their high index plane and surface structure, grain boundary formation, also even in powder cases, those CO2 to CO conversion generate certain pH conditions. So there is local pH gradient, and that also detrimentally affects the performance of CO2 conversion. So one of my students come up with a very interesting idea I just showed you before, making this hierarchically porous gold structure so we can avoid all those issues. So we can increase highly active sites, also reaction sites, and also because it has macropores and nanopores, those three-phase transition of CO2 to CO, it requires liquid movement and gas bubble movement. And then this hierarchical structure is very efficient mass transport. Also, those generated CO bubble is very easy. So because of that, we reported a very high selectivity, and also just for the material wise, using the same amount of gold, we can generate almost 4 times higher CO generation. So this is a work with Professor Jeon in our department. And this student, actually, after she finishing this, she moved to Professor Xiaodong Chen's group as an exchange graduate student. And then what Professor Xiaodong Chen's group's specialty at that time was the lithium-ion batteries rate capability. So everybody wants to use cell phone charged very fast, and so that's everybody's vision. So typically in lithium-ion batteries anode, because of the material thickness, the ion conductivity and electron conductivity, actually there's imbalances. So if you make a near current collector, if you can make ion conductivity better, if you can make electron conductivity better away from the current collector, you can make the charging discharging much faster. So after I met Professor Xiaodong Chen, we got some idea that, okay, we can make some density gradient 3-dimensional porous structure we can test that. So this is the example. After making 3D copper metal structure, we de-electroplating, and then we can make this type of, so more porous, less porous. So we can make all sorts of different density gradient structure, and then finally we realized much better performance of battery, and also we found out this overall diffusivity and charge transfer resistance is definitely beneficial with density gradient structure. So this is submitted, and probably you can see on the paper soon.
Yeah.
Okay, so because of time limit, I'll just quickly finish my final parts. So anyhow, so our group has making 3-dimensional structure using these phase mask, and this is and then after light passing through, this is diffraction. So people usually call this is forward Fourier transform, but if you have some target structure, it's almost impossible to design right phase mask. Actually, this is mathematically very difficult problem. And our group has currently working on some inverse design. So the first attempt was a genetic algorithm, and then now we are working on the auto-join method of which make those non-analytic solution problem we can solve. And also we are working with professors in postdoc. We are working on the machine learning too. And currently our center consists of those professors in our department and other universities. Actually, this project is about $1.5 million per year. And then our goal is, so far we just have certain phase mask, and we make certain structure. Just using that structure, we made the application. Now we just optimize target motif. So actually, using those inverse calculation, we find out the required mask which was unable to make before, and then using this mask, we make the target structure and we make the best performing materials. That's our current research goal in our center. And then this is the movie, but because time constraint, I'll just skip it. And then this is one example that we recently submitted to Professor Jong-Ah Shin. So this is the example that we can make certain 3D structure, but the symmetry of their array is almost impossible to make it straight. So, but using new auto-join method and inverse algorithm, actually this type of mask we never expect we can show certain 3D structure, but we successfully made this straight line new patterning capability. So with that, I think our center will keep prosper. And finally, I want to acknowledge and thanks my students and also former students, and still we are collaborating together. And thank you for listening. Yeah.
Thank you very much. A very nice talk. So let's have quick Q&A session. So question from the audience. You can leave your question in the chat room, and then I can convey the question to the speaker.
I have a quick question. Very nice talk, Professor Jeon. Can you elaborate on this inverse design of your mask to create a pattern that you want to have? That was the slide of the motif.
Yeah, exactly. So actually, this research has been, today I showed just auto-join method, but we are also working on the machine learning algorithm with the Professor Jun-Seok Roh at postdoc. Actually, he develops a new algorithm of machine learning of generally, I never thought max education can be help from the machine learning, but actually he found, because he's a meta surface specialist, and he found a certain solution, and his algorithm is amazing. So currently we are working on the second paper, trying this motif, and basically maybe this movie shows a little bit better. So yeah, basically we are dealing with, so find out how those structure affects this, and then we just keep moving back and forth, and then we give certain feedback loop and make better 3D structure finally. So maybe we can discuss further about these issues.
Oh, that's great. Thank you.